Namaskaram. In this session, again, we will continue the problems of Fourier series. These are the solutions of last homework. We know that this is the general Fourier series representation of a function f of x, of a periodic function f of x, defined in the interval c to c plus 2l. Also, we have seen that a special case of Fourier series, that means c equal to minus pi and 2l equal to pi. In this case, Fourier series representation like this. Okay, here function is defined in the interval minus pi to plus pi. In this session, we will see another special case of Fourier series. Okay, the another special case is 12 equal to 2 pi, but c equal to 0. So in general, our interval is like c to c plus 12. So what about this interval? Here c is 0 and the end value is 0 plus 12. 12 is 2 pi. So 0 plus 2 pi, that is 2 pi. That means a function is defined in the interval 0 to 2 pi, like that. Okay. So what is L? L in this case, L is equal to pi. So what is the corresponding changes in Fourier series? We know the original formula of Fourier series. Yes, this is the general formula of Fourier series in the interval c to c plus 12. Here now our interval is 0 to 2 pi and L equal to pi. So what happened? Fourier series become a naught plus sigma n equal to 1 to infinity a n cos n pi x by pi, because our L is pi. So you can cancel these two pi. And similarly, you can cancel these two pi. So this is cos n x. This is our Fourier series. And what about a naught? A naught is 1 by 2l. Here 2l is 2 pi. So 2 pi integral c to c plus 2l, that is 0 to 2 pi, right? And f of x dx. So this is our a naught. And similarly, what about a n? This becomes pi, 1 by pi. This becomes 0 to 2 pi f of x cos n pi x by l. L is pi, right? L is pi. So this becomes cos n x. Similarly, bn is equal to 1 by pi 0 to 2 pi f of x sin n pi x by pi, that is sin n x dx. Okay, so these are the analogous changes in Fourier series and Euler's formula. Yes, that's why a Fourier series is like this: a naught plus sigma n equal to 1 to infinity a n cos n x plus b n sin n x. We denote the Fourier series by s of x, and a naught is equal to 1 by 2 pi integral 0 to 2 pi f of x dx, and a n is 1 by pi 0 to 2 pi f of x cos n x dx, and bn is equal to 1 by pi 0 to 2 pi f of x sin n x dx. Okay, consider a problem. Find the Fourier series of f of x that is equal to pi minus x by 2 whole square, and this function is defined in the interval 0 to 2 pi. Okay, so first you have to write the Fourier series and also write a naught, a n and b n. Okay, so what is a naught? Yes, a naught is equal to 1 by 2 pi integral 0 to 2 pi f of x dx. So this become 1 by 2 pi integral 0 to 2 pi pi minus x square by 4 dx. 4 is a constant, you can take outside. So this become 1 by 8 pi. So 1 by 8 pi. The integral of pi minus x square, that is pi minus x cube by 3, divided by the derivative inside. The derivative is minus 1. Okay. Next you substitute upper limit or lower limit. So minus 3 constant, you can take outside. So this become minus 1 by 24 pi. When x equal to 2 pi, this become minus pi whole cube, minus when x equal to 0, this is pi cube. Okay, and this is minus 1 by 24 pi. And what is minus pi cube? That is minus of pi cube, right? Minus of pi cube. So this is equal to minus 1 by 24 pi into minus 2 pi cube. Okay, then we can cancel this. So this is 12, and this minus minus become plus. So our a naught is pi cube. Okay, you can cancel one more pi. So one pi is here. So this become pi square. So pi square by 12. Okay, so a naught is pi square by 12. Next you have to find a n. So a n is given by formula 1 by pi integral 0 to pi f of x cos n x dx. Here f of x is pi minus x square by 4. Okay. So 4 is a constant, take outside. So this become 1 by 4 pi integral 0 to pi pi minus x square into cos n x dx. Next, we are going to integrate this expression. Either you can apply integration by parts repeatedly, or you can apply the general rule of integration by parts, that is the Leibniz rule. Okay, this is our Leibniz rule. Integral uv dx is equal to uv1 minus u1 v2 plus u2 v3, etc. This upper suffixes for derivative and lower suffixes for integration. So v1 means integral of v, v2 means integral of v1, like that. Okay, u2 stands for derivative of u1, like that. And this is valid only when u raised to k equal to 0 for some k. That means after some derivative, the first term becomes 0. Then only you can apply this method. Okay, so anyway, here this pi minus x square is a polynomial. It has that property. After some finite number derivative, this term becomes 0. So I'm going to choose this as u and this as v. Okay, so first function is u. That means pi minus x whole square into v1. v1 means integral of cosine x. So integral of cosine x is sin n x by n. Okay, and minus u dash. U upper suffix 1 means derivative of this u. So that is 2 times pi minus x into minus 1. So this is the derivative. This is our u1. Okay, into v2. What is v2? v2 is the integral of v1. This is our v1. So what is the integral of sin nx by n? That is minus cos nx by n square. Okay, then plus derivative of this term. Already minus 2 is there. So minus 2 into what is the derivative of pi minus x? That is minus 1. Okay, so this is our derivative of this u1, that is u2, into this is v1, v2, next one v3. v3 means integral of this one. What is integral of minus cos nx by n square? That is minus sin nx by n cube. Okay, so and then limits are 0, 0 and 2 pi. Next we have to substitute upper limit and lower limit. Okay, then when x equal to 2 pi, this is pi minus 2 pi, that is minus pi square, but there is a term sin nx. So this become actually sin n into 2 pi. That means sin 2n pi. What is sin 2n pi? Yes, that is 0. We know that sin n pi is 0. So whatever be the integer, some integer times pi is always 0. Okay, so first term is 0. Then what about the second one? Yes, in second term, 1, 2, 3. There are 3 minus, so this become minus, right? Then 1, 2 is there, so 2 into, and when x equal to 2 pi, this become pi minus 2 pi, that is minus pi, right? Minus pi into, this become cos n into 2 pi, cos n into 2 pi divided by n square. Okay, then we have one more term, similar to the first case. When x equal to 2 pi, this is sin n 2 pi, that is 0. Okay, so the third term is 0. Minus next one, lower limit. Okay, similar to when x equal to 0, this term is sin 0. This also sin 0. So both are 0. Okay, so both the terms are 0. What about the middle term? Middle term, similar to the previous case, there are 3 minus. So minus 2 times, when x equal to 0, this is again pi into, when x equal to 0, this is cos 0, right? Cos 0 by n square plus. Okay, so this become 1 by 4 pi and minus into minus plus. So this is 2 pi. What is cos 2n pi? Cos 2n pi is minus 1 raised to 2n. And what is minus 1 raised to 2n? 2n is always even. So minus 1 raised to even, that is 1. Okay, so this term is 1. Clear? So into 1 by n square. And there are 2 minus signs. So this becomes again plus and 2 pi by n square. 2 pi by n square. Then combining, this become 1 by 4 pi. 2 pi by n square plus 2 pi by n square, that is 4 pi by n square. You can cancel these two 4 pi. So this become 1 by n square. So our an equal to 1 by n square. Okay. Okay, next you have to find bn. And bn is equal to 1 by pi 0 to 2 pi f of x sin nx. Here f of x is like this. So 4 is constant, you can take outside. So this become 1 by 4 pi integral 0 to 2 pi pi minus x square into sin n x dx. Okay. Next we are going to apply the Leibniz rule of integration by choosing first function as pi minus x square and second function as sin n x. Okay. So this integral become, okay, this is our u and v1 integral of sin n x, and this term is u upper suffix 1 derivative of pi minus x square. This is v2. v2 stands for the integral of v1, this entire thing. This is minus sin n x by n square, and this is u2. u2 means derivative of u1, and this is finally v3. v3 is the integral of v2, that is means minus sin n x by n square. Okay, then 0 to 2 pi. Okay, first we are going to substitute upper limit 2 pi. Then this become pi minus 2 pi, that is minus pi square, that is pi square. When x equal to 2 pi, as similar to the previous case, this is cos 2n pi. Cos 2n pi is minus 1 raised to 2n, that is equal to 1. Okay, so that's why this become minus 1 by n. There is a minus sign. And plus, when x equal to 2 pi, this is sin 2n pi. We know that sin 2n pi equal to 0. So the second term throughout 0. Plus one more term, that is 2 into minus 2 into minus 1, that is 2 times when x equal to 2 pi, this is cos 2n pi, that is minus 1 raised to 2n, that is 1. So this is 1 by n cube. Okay. So next we have to substitute the lower limit. When x equal to 0, this become, when x equal to 0, this is pi square into cos 0 is 1 minus 1 by n plus sin 0 is 0, second time throughout 0, plus this is minus 2 into minus 1, 2 times cos 0 is 1 by n cube. Okay. Next you have to simplify. So this is minus pi square by n, and this is 2 by n cube, and this is minus into minus plus, so pi square by n, and this is minus into plus minus 2 by n cube. So you can cancel everything, so this becomes 0. Okay. So all the vn's are 0. Now we are ready to write the Fourier series. So we know that the Fourier series is given by this formula a naught plus sigma n equal to 1 to infinity a n cos n x plus b n sin n x. Here a naught is pi square by 12, and a n is equal to 1 by n square, and b n's are 0. So this is the Fourier series representation of this function. And one more thing, actually this function is a polynomial, pi minus x by 2 whole square. We know that this function is continuous. So there is a relation between function and s of x. Yes, the relation is they are same. If it is continuous, then they are same. So we can write like this: pi minus x by 2 whole square is equal to pi square by 12 plus, like this. Okay. Anyway, this is the Fourier series representation of this function. Yes, so you can write ultimately pi minus x by 2 square is equal to pi square by 12 plus sigma 1 by n square cos n x. Okay. Okay, next we consider a general type of problem. Find the Fourier series of this function. Function is defined like this: minus 1 if x is in between minus 1 and 0, 2x if x is in between 0 and 1. Okay, so actually this function is defined in the interval minus 1 to plus 1. Hence evaluate this one. Okay, we know that our general Fourier series is defined in the interval c to c plus 12. Okay, so here our function is defined in this interval. So what is c and what is 12? Yes, for in this example, our c is the lower value, that is minus 1, and 12 is the length of this interval. What is the length of this interval? Yes, 1 minus minus 1, that is 2. So 12 equal to 2. So what about L? L equal to 1. Okay, so here c equal to minus 1 and L equal to 1. So we can write the Fourier series. Okay, so what are the changes in our Fourier series? Our interval is minus 1 to plus 1. So all the integrations are like minus 1 to plus 1 like. Okay, all the integrations are from minus 1 to plus 1. And what about the change in cos n pi x by L? Yes, in this case our L equal to 1. So this become cos n pi x, that's all, because L equal to 1. Okay, all the n pi x by L become n pi x. Okay, so this also n pi x. And one more change in this 1 by 12. Yes, we know that L equal to 1. So what is a naught? What is a naught? A naught equal to 1 by 2 into 1. Right? Integral minus 1 to plus 1 f of x dx. Similarly, a n 1 by 1 integral minus 1 to plus 1 f of x cos n pi x dx, because L is 1. Okay, so these are the analogous changes in Fourier series and respective formulas. Okay, so a naught equal to 1 by 2l. So 2 into 1, that is 2, minus 1 to plus 1, f of x dx. Okay, so our function is defined as two functions. So we have to split this integral as sum of 2. So this become 1 by 2, minus 1 to 0. In this interval, our function value is minus 1, plus in the second interval, our function value is 2x. So 0 to 1, 2x dx. Okay, so this become minus 1 into x, minus 1 to 0. This is x square by 2, so you can cancel that 2. So x square 0 to 1. So this become minus of 0 minus minus 1 plus 1 minus 0, right? So this is actually minus 1, okay, and plus 1, so 0. So a naught is 0. So next an is equal to 1 by l is 1, integral minus 1 to plus 1 f of x cos n pi x by l. Here l is 1, so cos n pi x dx. Okay, so again you have to split this integral as sum of 2. Yes, this is equal to minus 1 into in this interval f of x is minus 1, in this interval f of x equal to x. Okay, so next we are going to integrate. Okay, its integration become sin n pi x by n pi. Okay, so next we have to integrate this thing. Okay, so I'm going to choose this 2x as u and cos nx as v. And again you use the general rule of integration by parts. Oh sorry, actually this is n pi x. Okay, so the second one become first function 2x into integral of cos n pi x, that is sin n pi x by n pi, minus derivative of 2x, that is 2, into integral of this one, that is our v2. Okay, that is minus cos n pi x by n pi square, n pi whole square, that is n square pi square, and 0 to 1. Okay, okay, when x equal to 0, this is sin 0, sin 0, 0, and x equal to minus 1, this become minus sin minus n pi by n pi. Okay, and what is sin minus n pi? We know that sin minus theta equal to minus sin theta. So this become minus of sin n pi. And what is sin n pi? That is 0. So this term also 0. Okay, then next term. Okay, when x equal to 1, this is 2 into sin n pi by n pi, plus, because minus into minus, plus 2 into cos n pi by n square pi square, minus, and x equal to 0, this time is 0, and minus into minus, plus 2 into, this is cos 0 by n square pi square. And we know that sin n pi is 0 and cos n pi is minus 1 raised to n, right? And this cos 0 equal to 1. So this become, and 2 by n square pi square is common, you can take outside. So remaining time is minus 1 raised to n minus 1. Okay, so this is our n. So Bn is given by 1 by l is 1, minus 1 to plus 1, f of x sin n pi x dx. So we can split this integral as sum of 2 like this. So integral is like this. This is minus cos n pi x by n pi, minus 1 to 0. And here we choose this as u, 2x as u, and sin n pi x as v. So first function into integral of second, minus derivative of this into integral of this. Okay, and 0 to 1. Next we have to substitute the all upper limit and lower limits. So when x equal to 0, this is, okay, minus into minus plus. When x equal to 0, this is 1 by n pi, minus. When x equal to minus 1, this is cos minus n pi by n pi. Okay, plus here when x equal to 1, this is, there is a minus sign, so that's why this is minus 2 into cos n pi by n pi, plus minus into minus plus 2 times, and this is sin n pi by n square pi square, minus when x equal to 0, some 0 times, so this term is 0, and this is sin 0, that also 0. Okay, and here we know that cos minus theta equal to cos theta, and cos n pi equal to minus 1 raised to n. So this is actually cos n pi, and that is minus 1 raised to n. So this become 1 by n pi minus 1 raised to n by n pi, and now this term is minus 2 times. What is cos n pi? That is minus 1 raised to n by, that is n pi, and sin n pi, that is equal to 0. So that's all. So okay, here 1 by n pi is common, you can take outside. So this term is 1, and there is a minus of minus 1 raised to n, and minus 2 times minus 1 raised to n. Combining these two, this become minus 3 times minus 1 raised to n. So this is our Bn. Now we have a0, an and bn. Now we are ready to write the Fourier series. So here our Fourier series is a0 plus sigma n equal to 1 to infinity an cos n pi x, because here L equal to 1 plus bn sin n pi x. Okay, so here a0 is 0, so our Fourier series become, okay, so this is the Fourier series of this function. Okay, then next one. Next we have to evaluate this infinite series. Before that, what is the relation between this f of x and s of x? You just draw the curve this f of x in the interval -1 to +1. Okay, this is the rough sketch of this function. In the interval -1 to 0, our function value is throughout -1. When 0 to 1, function value is like 2x. We know that y equal to 2x is a straight line like this, almost like this. Okay, anyway, this point is 1, 2, right? When x equal to 1, y value equal to 2. Okay, then my question, then what is the relation between this s of x and f of x? They are same or not? Yes, it is clear that there is a discontinuous point at x equal to 0. Except 0, this function is continuous. Okay, so s of x equal to f of x if x not equal to 0, right? When x equal to 0, what happened? Yes, this is a jump discontinuity, so that is nothing, f of 0 plus f of 0 minus divided by 2. What is f of 0 plus and f of 0 minus? Yes, when x tending to 0 through right side, then function is tending to 0, so this is 0. And what is f of 0 minus? When x tending to 0 through left side, then function is throughout constant, that is -1, so this value equal to -1. Okay, so this is actually 0 plus -1 by 2, that is -1 by 2. Okay, so this is the relation between f of x and s of x. S of x is equal to f of x when x not equal to 0. When x equal to 0, our s of x is equal to -1 by 2. Okay, that means when we substitute x equal to 0 in this infinite series, that sum is converges to -1 by 2. That's all. Okay, anyway, next we have to evaluate this infinite series. First, from your observation, it is clear that terms like 1 by n squares belongs to this first term. The second term contains only terms like 1 by n and n pi like that. Okay, so which value of x is suitable from this interval? We know that x is varying from -1 to +1. Which value of x gives almost a series like this? Yes, from our first observation, it is clear that when x equal to 0, this all terms become vanishes, because when x equal to 0, this is sine 0. So all these terms are 0. So we are going to try. So we are going to try by substituting x equal to 0. So when x equal to 0, what about s? Yes, we know that s of 0 equal to -1 by 2. Okay, from this expression, what is s of 0? When s equal to 0, this become sigma n equal to 1 to infinity. Okay, so s of 0 become sigma n equal to 1 to infinity 2 by n square pi square -1 raised to n minus 1 into cos n pi 0. That is cos 0. We know cos 0 is always 1. Plus this expression into sine 0. What is sine 0? That is 0. Equal to -1 by 2. Okay, so next we are going to expand this infinite series. Okay, when n equal to 1, this is 2 by 1 square into pi square. When n equal to 1, this is -1 minus 1, that is -2, right? -2. Plus when n equal to, what happened? This is -1 raised to 2, -1 raised to 2 minus 1. What is -1 raised to 2? That is 1. So 1 minus 1, 1 minus 1 equals 0. That means for even powers of n, this term always 0. Okay, so 0. Then what about when n equal to 3? When n equal to 3, again it is 2 by 3 square pi square into -2. Clear? Plus etc. equal to -1 by 2. Now it is clear that here -4 by pi square is common. So you can take outside. And the remaining term is, here it is 1 and this become plus 1 by 3 square, right? 1 by 3 square. What about the next term? Next non-zero term is 1 by 5 square plus etc. equal to -1 by 2. Then this infinite series is equal to this. So by cross multiplying this term to right side, so this infinite series is equal to -1 by 2 into minus pi square by 4. That is pi square by 8. So its value is equal to pi square by 8. Okay. This is our Fourier series. And by substituting x equal to 0, now we have the value of this infinite series equal to pi square by 8. Okay. So this is your homework. Thank you.